Tonight we're going to learn something about the future, probably not about fire alarms, but the future of the universe. And tonight's speaker is Dr. Matt Bothwell from the Institute of Astronomy at the University of Cambridge, just across the road. On Wednesday night he runs outreach events there every week, so he's just saying to me he's normally in my role. So Matt's an astronomy communicator and science writer at the Institute of Astronomy at the University of Cambridge. He gives public lectures and writes about all things astronomical, as well as helping academics to improve their science communication skills. He received his PhD from Cambridge in 2011, and as a researcher, he's interested in the role of gas and star formation in the evolution of galaxies across cosmic time. In 2017, he left full-time research to focus on science communication. His science writing has appeared online in the Daily Beast and the Aeon magazine, and his first popular astronomy book, The Invisible Universe, Why There's More to Reality Than Meets the Eye, was published in 2021, November. So I'm going to hand over to Matthew now. Please welcome him.
Wonderful. Well, hello everyone. Thank you for giving up an evening to come and hear about the future of the universe. We've got about 40 minutes to cover the next 10 trillion years or so, which should be absolutely fine. So the story starts here. So today's talk is going to be all about cosmology. And probably lots of you have heard that word before, of course. Cosmology is the study of the entire universe. It's subtly different to astronomy. I often say that astronomy is the study of the things inside the universe, whereas cosmology is the study of the universe as a whole. So asking how big is a star or how old is a galaxy is an astronomy question. Asking how big is the universe or how old is the universe or what shape is the universe or the future of the universe is a cosmology question. And the story of modern cosmology really starts here with our Milky Way galaxy. If you went back in time around 100 years to the 1910s, the 1920s, an astronomer would have told you that a picture like this was a picture of the entire universe. It was the sort of conventional belief that the Milky Way was the only object in the entire universe. That began to sort of totter a little bit because there are these things which astronomers call nebulae, which are nebulae just is Latin for cloudy thing. And the more we learned about our galaxy, the more we began to wonder if these little nebulae in the sky weren't actually little cloudy things inside of our Milky Way, but if they were actually entire galaxies. And what really set the stage for all of modern astronomy was a debate on this topic, which is kind of amazing if you think about it. The way they used to settle scientific debates in the olden days was actually get two scientists into a room and they would argue it out like a boxing match in front of a paying audience. Like this is true, this actually happened. This is called the Great Debate in Astronomy. It's between these two guys, Harlow Shapley and Heber Curtis, two of the most famous astronomers 100 years ago. And this happened in Washington, D.C. People literally bought tickets to go and watch these two guys argue about the size of the universe. So Shapley was arguing that the Milky Way is the entire universe, which was the sort of the conventional view of the time, and Heber Curtis was arguing for this sort of slightly dangerous new idea, the idea that the Milky Way is just one galaxy among many galaxies, and these little whirly things in the sky are sort of twins of the Milky Way. It's actually really interesting. If you go back and read their arguments, one of Harlow Shapley's main arguments was just how stupidly big the universe would have to be if these little whirly clouds were other galaxies, because we knew the Milky Way was 100,000 light years across. And, that's already, 100,000 light years is a long way, right? So we realized if these little whirly clouds were galaxies, they would have to be millions of light years away. And the idea of a universe millions of light years across just was too much. So, one of Harlow Shapley's main arguments was just, no, the universe can't possibly be millions of light years across. That would be ridiculous. But of course, he was wrong. Heber Curtis was right. I'm skipping to tell you what you already know. Of course, and we've known for more than 100 years now that the Milky Way is just one small part of a much, much bigger universe. The important thing for today's lecture was how this was settled. It wasn't actually settled at the time of the debate. Everyone probably went home kind of unsatisfied. But the answer came a few years later when this guy, Edwin Hubble, who you've probably all heard of because of the Hubble Space Telescope was named after him, one of the most famous astronomers of the 20th century, he measured distances to these little galaxies for the first time and proved that they were actually millions of light years away. And so they had to be outside of our galaxy, and so our Milky Way was sort of reduced to a tiny dot in a much, much bigger cosmos in one go. It got more interesting very, very quickly after that, though, because we already knew, and we had known for more than 50 years at that point, that these little whirly clouds were all moving away from us. And when we thought they were little clouds inside of our own Milky Way, it was we didn't understand why, but it was explicable, right? The idea, there were various theories, like maybe they were being ejected from the center of our galaxy, or maybe they're being pushed away by the starlight of the Milky Way or something. There were various theories, but as soon as it came along that they weren't little clouds being spat out by the center of our galaxy, they were entire galaxies, explaining why they were moving away from us gets a lot more tricky. And the real breakthrough came from Hubble when he took the speeds of the galaxies, which we'd already known, how fast these galaxies were moving away, and compared them to the distances, and made this very famous plot with speed on the y-axis on the left and distance on the x. And he found that there was this nice linear relationship between speed and distance. This is a graph from 1929. And so galaxies aren't just sort of moving at random. There's this predictable pattern where everything's moving away from us, but in this way that the more distant things are moving away from us faster. And that is smoking gun evidence of being in an expanding universe. And so this is what Hubble figured out in 1929, so we are just coming up on the 100th anniversary of figuring out that the universe is expanding. You almost feel sorry for astronomers at the time, like they'd only just had their minds blown by discovering the universe is billions of times bigger than we previously thought, and now they get told it's actually just getting bigger and bigger and bigger all the time. Transformative time. Anyway, so the discovery of the expanding universe led to the discovery of the Big Bang. Because of course, if the universe is getting bigger and bigger and bigger, it stands to reason there was some moment that kicked it off, right? So the discovery that the universe is expanding led to the discovery of the start of the universe and basically most of 20th century astrophysics. The Big Bang and the expanding universe that underpins all modern astrophysics is nothing makes sense without it. It's as important to astrophysics as the theory of evolution is to biology, right? Everything that we know about the modern universe is underpinned by this idea of an expanding universe. But the question we want to ask, the question in the title of today, is what happens in the future? Given that we know that the universe is expanding, what does the future of the universe look like? So if we call the Big Bang time 0, and we're here 13.7 or so billion years later, what does the far future look like? What does the universe look like in hundreds of billions of years, or even trillions of years? Well, on the largest scales, what really matters is the expansion of the universe and gravity, right? Those are the forces that really matter, that you have to think about when you're understanding the universe. And around the 1990s, astronomers started to wonder, well, we can see the universe is expanding. We know that right now the universe is getting bigger, but we also know that gravity is a thing. Gravity exists and is a universal force that tries to pull things together. And so gravity, at the very least, should be acting as a brake on the expansion of the universe and should be slowing down the universe's expansion. And so this is where everyone got to in the sort of the 1980s, 1990s. The expansion of the universe is probably slowing down because of gravity pulling everything back together. And the big question was, how much is the expansion of the universe slowing down? So we can do a thought experiment at this point to think about the expanding universe in maybe a more intuitive way. So imagine going out into a park and throwing a ball in the air. And so the question is, what happens next? And the answer, of course, depends on how hard you throw the ball, right? If you throw the ball in a normal way, the ball is going to do something like this. It's going to go up and up and up and up and up, but the whole time, Earth's gravity is pulling on it, and it's slowing down, and it will eventually reach some maximum and then start falling down to Earth. And to make it explicit, right, this isn't like throwing the ball is like the Big Bang, that the height of the ball above the ground is like the size of the universe, and so the universe is expanding as the ball goes up, but the whole time gravity, either the gravity of the Earth or the gravity of all the galaxies, is pulling it back together, and it slows and slows, eventually reaches some maximum, and then is pulled back down to Earth. So this is sort of one potential, maybe slightly pessimistic life story for the universe. Alternatively, if you could throw the ball much faster, if you're Superman or something, you could throw the ball and so it escapes into space, right? The Earth has a sort of set escape velocity. If you throw the ball hard enough, you could throw the ball so fast, it just escapes Earth's gravity and disappears off forever. And so this is another potential future for the universe, right? So if we make this like a tiny bit more scientific, rather than talking about Superman throwing a ball in the park, we can make a graph of the sort of average scale of the universe, or the average distance between galaxies over time, right? These are two different ways of measuring the same thing, the average size of the universe and the average distance between galaxies over time. And what we know, so what Hubble found, like our data point from the 1920s, is that we are currently on an upward trajectory. So we'll say we're at some sort of arbitrary time here. We'll say right now the universe is getting bigger. So we're going right because time going forwards, and we're going up because the universe is getting bigger. And so one potential history for the universe is the Big Bang, then the universe gets bigger and bigger and bigger, but the whole time the expansion is slowing because of gravity acting on it. And then right now it's still expanding, but at some point in the future it will reach some maximum size, and then gravity will start to win, and the universe will contract and shrink smaller and smaller and smaller, and until there is some sort of anti-Big Bang, what astronomers call a big crunch, the universe just sort of getting crushed down to nothingness. And of course, if you are a person that lives in the universe, you might want to ask, like, is this going to happen, right? And when is the universe going to be destroyed? Alternatively, like, maybe the more optimistic version is like the Superman throw universe, where the universe starts in a Big Bang and then gets bigger and bigger and bigger, but there's just not enough gravity to pull it back together. There's not enough stuff in the universe to overwhelm the expansion, so the universe just gets bigger and bigger and bigger with time. And so these are the two sort of potential life stories of the universe. We could live in a sort of a blue, big crunch, doomed universe, or we could live in a red universe where there's not enough stuff in the universe to resist the expansion, and so it just gets bigger and bigger and bigger forever. So what we want to do, so this is my sort of slightly dodgy cartoon graph, right? But it contains a nugget of truth. So you'll notice that these two paths, as well as being different in the future, because that's the question we're trying to answer, right? What's the future of the universe? Are we headed for a big crunch or not? But they also differ in the past. And so what we need to do is look back in time and measure the average scale of the universe, the average distance between galaxies in the past. And if we do it accurately enough, we should be able to tell if we're on the blue track, heading for a big crunch, or if we're on a red track, heading for a nice sort of drifting expansion forever. And this sounds slightly science fiction-y, right? Looking back in time and measuring the universe, but of course every astronomical measurement is a measurement back in time. If you look 1 million light years away, you're looking 1 million years back in time. If you look 1 billion light years away, you're looking very, very far back in time. So in order to measure the average scale of the universe in the past, all you have to do is look far enough back in time and make sort of several measurements at different ages of the universe, and in theory, you should be able to tell which one of these tracks you are on. So the way we do it, so this experiment was actually done. It was done in the 1990s. It's called the Supernova Cosmology Legacy Survey. It's called named after supernovae because of the way they chose to measure distances between galaxies. So, like, measuring distances in astronomy is fundamentally quite hard. It's hard to look in the sky and see how far something is away. Astronomers can use a particular type of exploding star as a beautifully accurate distance estimator. It's called a supernova 1A. And so you might have heard the word supernova. It's when a star explodes at the end of its life. A supernova 1A is different, though. So it's what happens, you only get it from a white dwarf when a white dwarf is orbiting around a regular star. Now, white dwarfs have this particular property, which is that if they get too big, they explode. And this mass limit is about 1.4 times the mass of the sun. And so a white dwarf on its own, that's, say, just equal to the mass of the sun, will happily sit there forever. But a white dwarf that's in orbit around a regular star and accreting matter from it will get sort of bigger and bigger and bigger until it crosses this threshold and trips this mass limit and explodes. And these are fantastic for astronomy for a couple of reasons. First of all, they are extraordinarily bright. So if one of these goes off anywhere in the universe, we see it pretty much. One of these goes off in a galaxy 10 billion light years away, we see it. But the other reason astronomers love these is because the laws of physics that dictate this exploding white dwarf, are actually relatively simple. And so we can be very confident that every single white dwarf in the universe that explodes like this is exploding with the same energy. And so we know exactly how bright that explosion is. And so we can use it as a standard candle. We see one of these things going off. We know exactly how much energy is in that explosion, which tells us exactly how far that thing is away, right? So these are some of these beautiful distance estimators. So we're sitting in the galaxy. One of these things goes off. It immediately tells us, this is a terrible drawing, isn't it? This is not to scale. It immediately tells us how far that galaxy is away. And so these Supernova 1a are, these golden things for physics. And so the way they did the experiment, they started off nearby because those are the easiest things to see, and they got further and further and further away. And I want to show you the data as it came in, like give you the experience of the team kind of collecting this data. It did something like this. My computer's not happy. There we go. It did something like this, which was very, very surprising. Remember, the whole aim of the game was to work out, are we on the blue track or the red track? And it turns out the answer is neither. We're very much not heading for a big crunch universe, but we're also not heading for a universe that just seems to sort of drift and drift and drift. So what's going on? The universe seems to be accelerating. It's speeding up. So to go back to our throwing a ball in the park analogy, this is a bit like you go and you throw a ball, and the ball just sort of gets faster and faster and faster, and then sort of whooshes off into the clouds. And like it sounds like I'm being ridiculous, but that is very literally what we see happening to the universe. There is something that we don't understand pushing the universe apart faster and faster and faster. We have an accelerating universe. Like something has its foot on the accelerator pedal of the universe, some sort of force. We have no idea what it is. We could end the talk here, right? You're basically up to date with modern physics. We know this thing exists. We have no idea what's going on. I'm going to spend the rest of the talk telling you our best guesses. Everything from here forward has a speculation warning. Like this is observed. Everything forward from this is on pretty shaky ground. It's very difficult to know. Okay, so we call this force dark energy. It does, because it has a name, doesn't mean doesn't mean we actually know what it is, doesn't mean we've explained it, we've just given it a name. It's also nothing to do with dark matter. It can be very confusing. The problem is astronomers use the word dark to mean I don't understand this thing, right? So dark matter is matter that we don't understand. Dark energy is energy that we don't understand. There is some sort of energy in the universe that we can't measure directly, but which is pushing the universe apart at the seams. So the really big question is, what is this? Like, what is this dark energy? How can we not notice it in everyday life, but it's so powerful it can push the universe apart at the seams? And is there any reason to expect this? Like, if we go to our physics textbooks, our physics theory, is there any reason to expect this? And surprisingly, the answer might be yes. Something like dark energy, which was actually predicted more than a century ago by Einstein, but he sort of went back and then called it his greatest mistake. So just to kind of fill you in on some of the background. So I told you that around a century ago, we thought the Milky Way was the only thing in the universe. We also thought that the universe was infinitely old and unchanging, right? And the discovery of Hubble's expanding universe only came after Einstein, which I always find amazing, right? Einstein was writing down these equations of space and time. He thought he lived in a tiny static universe. It was only after Einstein's theory that we actually worked out that the universe is expanding and changing and began with a Big Bang. And this was actually a problem for Einstein, because Einstein wrote down his equations of general relativity in 1915. And these equations, which are still absolutely fantastic, they've been tested to like 15 decimal places and they work beautifully. Einstein's equations seem to imply a universe that was like changing. Like Einstein's equations inherently describe a dynamic universe that wants to grow or shrink. And this really bothered Einstein, because Einstein wanted a static universe. Einstein thought he lived in a frozen, tiny universe. And so he was very confused when his lovely equations seemed to describe a universe that was growing and changing. And so what he wanted to do was to sort of force his equations to describe a static universe. And so if we take this, which is the universe, I'm going back to terrible diagrams, I'm afraid. So Einstein knew, okay, we have the universe here, and his equations told him that the universe was sort of changing over time. And so what he figured was, okay, well, we have the universe, and gravity is trying to like pull everything together, because that's what gravity does. But in order to keep the universe static, in order to keep the universe sort of unchanging, which is what he thought, he invented this new force to push back against gravity, which he called the cosmological constant. Like, it wasn't a natural part of the equations, right? The equations told him that the universe is changing, and he thought, no, I don't want that. I want a static universe. And so he invented, just completely out of nowhere, this new thing called the cosmological constant, which is this sort of pushing force in space, pushing out, pushing back against the contraction of the universe, against gravity. It was a bit of a kind of an ugly sort of kludge. He was never very happy with it. Like the equations that describe the universe, like the equations of general relativity, are very elegant and very nice. The cosmological constant is very much just like a kind of plus blah, just plonked into the equation because he wanted to keep the universe static. So he was never very happy with it. So I think he was probably delighted when Hubble came along and told him, you don't need the cosmological constant. You can throw away the cosmological constant because the universe is actually changing with time. Like, your equations were right all along. You don't need to have this sort of completely invented factor in the universe pushing back against gravity. So Einstein was delighted and sort of got rid of his cosmological constant and called it his greatest mistake. Except it now looks like the cosmological constant might be real, right? So the cosmological constant, if you think about what Einstein intended it to do, was to push back against gravity. He knew the universe wanted to collapse, and so he invented this sort of springy pushing force in the universe to resist that. And it happens time and time again. Like, so a physicist wrote an article about 10 years ago called "The Cosmological Constant Refuses to Die." Basically, it gets resurrected again and again and again all throughout the 20th century to solve problems. And until now, they've all been kind of illusions. We've never actually needed it. But now, with the results from the Supernova Cosmology Legacy Survey, the results that the universe seems to be speeding up, it really does seem like the cosmological constant is here to stay. There is some sort of springy, pushy factor to space, making it expand faster and faster and faster. So yes, Einstein's greatest mistake probably wasn't Einstein's greatest mistake. So that's why Einstein's great, right? Even when he thought he was wrong, he was actually predicting physics 100 years into the future. The really, really big question is, though, what actually is the cosmological constant? Like, Einstein never got into the nitty-gritty of how there could be a sort of springy pushing force built into space-time. He just sort of said, imagine there was. Imagine that space-time had some natural push, and then this would work. And so that is kind of what we see. We see that space-time has some natural push. But what we want to do, we want to be better than that. We want to kind of get into the nitty-gritty of how that might actually work. And it turns out there is some precedence for this as well. There are some equations which come from a completely different branch of physics that might make this work. So you have to kind of leave the cosmological realm, the realm of the very big, and go into the quantum world where everything's really, really small. So if you go and find a friendly quantum physicist and ask them a question, they will tell you that quantum theory predicts something that looks a lot like a cosmological constant. It all comes down to this idea that there is some sort of inherent energy attached to space. So you might have heard of something called the uncertainty principle in quantum mechanics, and there are certain quantities that you can't say for sure, right? So one of them is energy. You can't be exactly certain about how much energy is in a little box of space. And so if you take a patch of completely empty space, you fly outside the Milky Way, you've got a little patch of empty space in front of you, and you say, well, how much energy is in this space? The answer should be 0, except that's an exact number, and you can't have exact numbers according to quantum mechanics. And so there is this sort of small amount of energy associated with empty space, according to quantum mechanics. And the way this is like actually manifested in the real universe is in terms of what physicists call virtual particles. So like modern quantum physics, this sounds bonkers, but it's true. Modern quantum physics models space as this sort of constantly fizzing, bubbling sort of thing of virtual particles popping in and out of existence all the time. Basically, you can create particles as long as you get rid of them before the universe notices. And that is happening all the time, according to quantum physics, and if you do your maths, that energy attached to empty space will push outwards. Like the energy inherently built into empty space will sort of act as a cosmological constant type thing. Kind of, it gives space a natural springy pushing power. Which sounds great. It sounds like we've solved the problem, right? We have a theoretical prediction from Einstein that there's a way for space to have some springy power, and we go and find a quantum physicist, and they tell you, yes, our equations still do tell you that space has some springy pushing power. They worked this out in the 1980s. And now we go to the actual universe, and we see the actual universe is being pushed apart faster and faster and faster, as if space has some springy pushing power. So it almost sounds like it's just time to collect our Nobel Prizes and go home, right? Except there is a kind of tiny wrinkle, which is that the theoretical predictions from quantum physics get the answer wrong. So you can work out how strong the effect is in the real universe, right? You look at the galaxies and see how fast they're being pushed away by this dark energy force, and you can compare the strength of that force with what quantum mechanics says should be the strength of that force. And it gets the wrong answer. And by wrong, I do mean very wrong. And by very wrong, I mean the wrongest anyone has ever been about anything. It's the biggest discrepancy between theory and experiment in the history of science. So to make it explicit, quantum theory predicts dark energy, a stronger dark energy than we observe in the real universe. So quantum physics predicts more dark energy than we actually observe. And it's more by this amount. So that's 10 to the power of 120. So something has gone very wrong, right? So dark energy this strong. So if dark energy actually was 10 to the power of 120 is an unbelievable number, right? There's no number in our everyday existence that comes anywhere close to here. There's about 10 to the power of 80 atoms in the observable universe, right? So this is like a bigger number than we ever have any reason to deal with. And so a dark energy this strong would blow the entire universe up until it was, trillions of light years across in a millisecond, right? If dark energy actually was this strong, then a nanosecond after the Big Bang, there would be sort of one atom per observable universe, right? Because it would have got blown up so big. So the really big question is, why didn't anyone worry this in the past? I told you this calculation was done in the 1980s. This seems a big deal, right? Quantum physicists in the 1980s predicted that the universe basically shouldn't exist because it blows itself up to ridiculous size within a millisecond. So why didn't people worry about this in the past? Because, they are observers as well. They could look around and see that the universe does actually exist, right? Who seems to disagree with the equations. And the answer is that people sort of expected that there was a sort of hidden multiply by zero somewhere waiting to be found, which has happened before, right? It doesn't really matter how big a number is, if it's multiplied by zero, it becomes zero. So yes, even if you have this ridiculous sort of 10 to the power of 120 strength dark energy, you multiply it by zero, it becomes zero, you go home, it's fine. So people just assumed that there was a sort of hidden multiply by zero somewhere in the equations, which they hadn't found. But we now run into a really, really serious problem, which physicists don't know how to explain, which is that when it turns out it's not a multiply by zero. It's a multiply by 10 to the power of minus 120. And this is a ridiculous number. There's no reason that a number like this should exist in nature, right? There's no other physical law anywhere that includes a multiply by 10 to the power of minus 120. Taking the massive number and turning it into zero just needs a mathematical blunt instrument, right? Just multiply by zero and it's fine. This needs an incredible amount of fine-tuning. And so this is what physicists call the fine-tuning problem. So it's the fact that we see dark energy, there's a prediction for how strong dark energy should be, but there seems to be some sort of missing factor which brings the predicted value down to the real value we have in our universe with just absolute pinpoint precision. Because if you imagine you're sort of sitting there controlling the universe and you've got a dial called dark energy, you really don't have to turn that dial very much before the entire universe just kind of blows up and there's no structure or galaxies or life formed. If instead of multiplied by 10 to the power of minus 120, it was multiplied by 10 to the power of minus 115. That means dark energy would be 100,000 times stronger than it is in our current universe. The universe would blow itself up and there would be no galaxies and no life. So it really seems that the universe is fine-tuned to produce structures like stars and planets and galaxies and life, because you need this incredibly precise number. If this was just a tiny bit bigger, no life. And this is a real problem, right? Physicists don't like fine-tuning problems. We don't like to think that our universe is special for some reason, right? We want the laws of physics to seem natural. But it really seems, when we look at dark energy, it seems like our universe is sort of precisely set up for life. And this is an unsolved problem. We don't know the answer to the fine-tuning problem. I think it's the kind of thing that keeps physicists up at night. I'm going to tell you my favorite solution, which I hope is true, because I think it'll be interesting. So the question is, why do we have this universe which contains this very, very, very precise amount of dark energy that allows structure and complexity and life to exist? Let me ask you a slightly different question. Imagine that the only thing in the universe was the Earth and the Sun. Is it a coincidence that the Earth is at the right distance from the Sun to create life? Right, so we are about 150 million kilometers from the Sun, which means that the temperature and the conditions on Earth are perfect for life. Is that a coincidence? And in the past, might have thought yes, but of course the answer is no, and it's not a coincidence because there are hundreds of thousands of millions of planets, right? And we just happen to have evolved on the one which is suitable for life. In the past, people spent a long time trying to work out why the planets were positioned just so in our solar system. There's a guy called Kepler, a very famous astronomer, spent an enormous amount of his career trying to work out the precise mathematical arrangements for the planets, because they thought the solar system was the only thing in existence, right? The solar system was the pinnacle of creation, and we had to work out all the laws that went into positioning the planets just so. And we actually know the answer now, and it's not an answer that Kepler would have liked very much. The answer is, it's basically just random, right? There are no laws, and there are just hundreds of thousands of millions of solar systems, and we just happen to have ended up with this one. If we were the only solar system in the universe, then yes, the reason we are the exact right distance from the Sun might need some explaining, but because there are hundreds of thousands of millions, then it doesn't need explaining at all. We just sort of won the cosmic lottery by being here. And so a lot of physicists think exactly the same answer might apply to our universe. We seem to have this universe that won the cosmic lottery, right? We are precise and fine-tuned for life down to this 10 to the power of minus 120 level, which is unbelievably precise. And if we're the only universe, then that's completely impossible to explain. Unless we have the same answer that we gave to Kepler, if we are not the only universe, and there are, in fact, hundreds of thousands of millions of universes, all with different values for dark energy, sort of set by the conditions of the Big Bang, then the problem goes away. We just, in the same way that we live on a Goldilocks Earth, one of hundreds of thousands of millions in the galaxy, we could well live in a Goldilocks universe, one of hundreds of thousands of millions or even trillions of universes, all with different sort of parameters for physical values. And yes, maybe the universe next door does have too much dark energy and it blew itself up just after the Big Bang and it's completely lifeless. But our universe has exactly the right amount, and so we live in it. So, of course, I'm not saying this is like the multiverse theory is absolutely true, right? This is just one theory, but it is really, really difficult to explain why our universe seems so fine-tuned for life. And dark energy seems to be full of these coincidences. So I called the talk "The Future of the Universe," And if our current understanding of dark energy is correct, then the future of the universe is just the universe being pushed apart faster and faster and faster and faster. And the gaps between everything will grow and grow and grow. I mean, so right now it's about 2.5 million light years to the nearest galaxy. In billions of years' time, that will just be an enormous amount, right? So the universe just gets emptier and emptier and emptier. So in the future, the amount of dark energy will just increase and increase and increase. And so sort of right near the Big Bang, the universe was almost all matter and basically no dark energy. In trillions of years in the future, there will be almost no matter because it will be so diluted, like putting one glass of squash into a swimming pool or something. The matter will be very diluted, but the dark energy will be completely dominant. But right now, there seems to be about the same amount of dark energy and dark matter. And again, we have no idea why. Why do we, the sort of intelligent observers, happen to live at the exact moment in the universe's history when dark matter and dark energy are perfectly balanced? We honestly don't know. We don't know the answer. Dark matter is full of these strange... dark energy. I'm making a mistake now. Dark energy is full of these sort of strange fine-tuning mysteries. And I think physicists can be slightly excused because we've only just discovered dark energy about 20 years ago, which is sort of a blink of an eye compared to astronomical history. We've known about the expanding universe for around a century, and 20 years after we discovered the expanding universe, we still didn't really understand it properly. So 20 years after discovering dark energy, we still don't really understand it properly. But the future is very, very bright. And I think particularly bright for people your age that are interested in these big cosmological ideas, because over the next decade or so, there are lots of facilities and new instruments that are going to be launched specifically trying to understand dark energy. The one we're looking forward to next is a satellite called Euclids, which is going to make the most extraordinarily detailed map of the universe. It's going to map the cosmic web and the distribution of galaxies all the way around the sky, and we'll be able to use that map to compare to our theory of dark energy, and that will actually let us start telling the difference between theories and hopefully teaching us a little bit about dark energy. It was supposed to be launched already. There was some political problems because it was a European mission. It was supposed to be launched on a Russian rocket, but now Europe and Russia aren't friends. So it had to be retooled for a different launch vehicle. But hopefully it will go up in the summer. So around this summer, this will be launched. Which means once it gets up there, starts calibrating, doing some data. Hopefully around 2025, 2026, it will start sending back some results, which means everyone your age, if you go on to be physicists and if you want to be cosmologists, just as you're starting your research careers, you're going to be absolutely flooded by this amazing data, the most accurate ever maps of the universe, which will hopefully reveal some secrets of dark energy, which we're all very excited about. Okay, I think I'm almost out of time, I think I'll leave you with one thing. I promised to tell you what the future of the universe was. And if our current understanding of dark energy is correct, which again might change, right? We still don't fully understand dark energy. But our current understanding is that dark energy will just get stronger and stronger and stronger, and the universe will just get bigger and bigger and bigger, faster and faster and faster for all of time. But what that means is that as time goes on, we're going to be able to see less and less and less of the universe. Right now, there's this concept called the observable universe, right? So the universe that we can see is a sort of a bubble around us, about 90 billion light years across. And anything that's further away than that is so far away, the light just hasn't had time to reach us in the age of the universe. And so the universe might go on, and almost certainly does go on, way beyond the observable universe, but we're sort of trapped within this bubble. But what the future of the universe holds is that dark energy will get stronger and stronger and stronger, and the universe will expand and expand and expand, and even more of the universe will be pushed over the cosmic horizon. So future observers will actually see the bit of the universe we can see, the observable universe, shrink and shrink and shrink. And so it's a bit of a strange thought if you can imagine any intelligent civilization in the Milky Way in maybe 200 billion years' time, which is a very long time, right? It's about more than 10 times the current age of the universe. But any intelligent observers in the Milky Way in a couple of 100 billion years' time might not know about the rest of the universe. The observable universe might have shrunk down to a bubble outside the Milky Way as the entire universe has been carried away by dark energy. And so people in the future might be forever trapped like those observers were 100 years ago, right? So people 100 years ago thought the Milky Way was the only thing in the universe and thought it was eternal. And that actually might be the state of affairs in the future. They might be stuck thinking the Milky Way is the only thing in the universe because dark energy has just carried the universe away. Which means that we are living at the perfect time in the universe's history to study it and get answers, which I think is a reason to be happy. And I've got to finish there. Thank you.
Thanks ever so much, Matt. That's great. We've got time for some questions now. So, if anyone has any questions, aha.
Right to the front.
Well, it might work.
Hello.
Hello.
So if like dark energy is something that is like all around, not all around, but everywhere, is there any way to like measure it on Earth, like how you can measure gravity?
It's a really good. Is the microphone working? Do you want me to repeat the question? Are we okay? Cool. Okay, so the answer is probably not, at least with any sort of feasible technology. So the way that dark energy works is that if it is this sort of intrinsic property to space, then it gets stronger and stronger and stronger the more space you give it, which is sort of bizarre, right? Because normally things dilute over bigger volumes, but dark energy just gets stronger over bigger volumes. But over small volumes, dark energy is actually amazingly weak. So like the force on your body due to dark energy is about the same as the force of like a single hydrogen atom sort of pinging against you or something. It is so far beyond our ability to measure at the moment. It's sort of completely unfeasible. Maybe in like 200 years' time.
Wouldn't the increase in energy going forwards be tempered or slowed by the decreasing temperature of the universe, approaching absolute zero?
I don't think it will have anything to do with the temperature of the universe. So you're completely right. So there is a sort of this photon background to the universe, which is currently about 2.7 Kelvin above absolute zero. As the universe expands and expands and expands, those photons get more and more diluted, and so the temperature is only going to go down. I think. So like photons, like which cause the energy in the universe, is what we call the radiation components of the universe. Like the important components of the universe to care about are radiation, matter, and dark energy. The radiation-dominated era of the universe was in the first sort of 100 million years or so, if that. You have to go way back in time to get to the radiation-dominated era. Like these days, radiation just doesn't play an important role in the evolution of the universe. So radiation only kind of like affected the overall evolution of the universe in the very earliest times, just after the Big Bang. We're already living in a time where radiation's become negligible from like a kind of cosmological energy point of view, and it's only going to get more diluted in the future.
So could the universe exist at absolute zero?
So I think it would never get to absolute zero. It will sort of asymptotically approach absolute zero, right? I don't think absolute zero is something absolute zero is like infinity, right? I don't think it's something you can sort of actually reach in the real universe.
I was just wondering, like, you were saying that dark energy is going to get like stronger and stronger, but like at this point we can't measure it on Earth and it doesn't have any effect on us. At what point, like billions and billions of years in the universe, is it just going to be like one atom per observable? Like, is it going to be that there won't be any intelligent life because just the atoms are too far apart to like do anything? Yeah,
that could well be true. I think it's hard to say these things for sure because we just don't understand dark energy enough. But yeah, there are some models of dark energy that say, yes, things will just be blown up until there's one atom per observable universe volume. And yeah, at that point, there won't be any intelligent life. There are, if anything, like even more pessimistic answers that basically say that dark energy will just get stronger and stronger until it just rips things apart. So it will get to the point where dark energy is just ripping apart the bonds between atoms and ripping apart the subatomic particles. I think it's because we don't have a good enough model of dark energy, it's hard to say for sure. If you're interested, by the way, a really good book recommendation on this is The End of Everything, which is a book by Katie Mack. So she writes about different ways the universe could end and talks about these sort of potential, like, different dark matter models. Some of these questions are what we're hoping that Euclid does, because right now we're faced with a phenomenon that we don't totally understand, so the best we can do is sort of educated guesses. Hopefully Euclid will do much better.
Lots and lots of questions. Okay, I'll take this one, and then...
If the universe is expanding, what would it be expanding into?
Yes, it's a good question. So if the universe is expanding, what's it expanding into? So nothing is a sort of really common answer to this. I think the problem is, my best answer is that the question doesn't really make sense, unfortunately. So there's nothing outside the universe. So when you think of the universe expanding into something, I guess you have this sort of model of a balloon being blown up inside a room, right? And the balloon is expanding into the room. But the problem is that there's no sort of space outside the universe for it to be expanding into, right? So the expansion of the universe is just the creation of space and time itself, right? The space-time fabric of the universe itself is expanding. I think a much better analogy than the balloon one, I really hate the balloon analogy, a much better analogy is, imagine you take the number line, so the number line 1, 2, 3, 4, 5, 6, 7, and that extends to infinity. If you multiply every number by 2, you've expanded the number line, right? You've expanded the number line by spreading them out, but it's not expanding into anything. There's no sort of beyond the number line, which is absorbing the new numbers or anything. You've taken an infinite thing and spread everything out. So you've expanded it, but it's sort of expanded from the inside. There's no such thing as the outside for it to be expanded into, if that makes sense. These things get very trippy, right? Because we're trying to understand sort of cosmological objects with our human brains that evolved to run around the savannah and run away from lions and stuff. And our minds didn't evolve to think about these cosmological things. So on some level, you have to just kind of trust the maths and accept that it doesn't make any kind of intuitive sense.
Okay. It's this hand first.
Hey, I was just wondering, do you think it's possible that rather than being dark energy that we don't understand, it's possible that our understanding of gravity is not full in the way that possibly over great distances it's actually pushing stuff apart, not pulling in?
Yeah, that's a really good question. So the question was, is it possible there's no such thing as dark energy and just gravity has some sort of anti-gravity repulsive force over long distances? It could absolutely true. This is an active area of research. It gets called MOND, which stands for Modified Newtonian Dynamics. It's the attempt to add some sort of repulsive aspect to gravity. As of right now, no one's been able to make the maths work, unfortunately. So in theory, yes, and I think you'd be crazy to rule it out, absolutely. But it's from what we can tell so far, the maths just absolutely doesn't work. There's no way to integrate that into gravity in any kind of consistent way.
Do you want to take some questions from the back? So I'm aware I keep asking questions at the front, so we want to give you a chance at the back.
Thanks. As far as I know, this was first kind of discovered by supernova observations by Perlmutter and people like that. Are there any other detection methods that we know of to measure the accelerating universe? Can you use the microwave background or anything else, or is it just supernova that we can measure it with?
Yes, so we absolutely can. Yes, so it was first discovered by these supernova 1A being a bit dimmer than they should be, which implies they're a bit further away than we expect, which means they're being pushed away. So that was done, like you said, Perlmutter and the Supernova Cosmology Legacy people in 2001. Those results came out. You can actually measure now dark energy in the cosmic microwave background. If you look at the CMB, I'll get a picture of the CMB for you, just so we know what we're talking about. If you measure the patterns in the CMB, sorry, bear with me. This will be worth it, I promise. So if you measure the patterns in the cosmic microwave background, so it kind of looks like this sort of modern art piece, if you break down the patterns, you get something called the power spectrum of the CMB, which is like a sort of a quantitative measure of the distribution of patterns in the CMB. And one of the sort of the big features that causes these patterns is dark energy. And so astronomers now, we can be pretty confident and we can say that the universe contains about, in terms of like the energy budget, contains about 30% matter and about 70% dark energy. And that's nothing to do with the accelerating universe. That's just measuring the patterns in the CMB directly, which is quite nice, right? It's quite nice when you have a completely independent measurement of something. But yeah, so both the accelerating universe and the CMB both tell you that there's an awful lot of dark energy out there.
What would happen if the universe touches another universe due to its expansion?
What happens if the universe touches another universe? It's a really difficult question to answer depending on how you're defining universe, because there are various definitions of universe, right? So there's the observable universe. That's what observational astronomers like me talk about when we talk about the universe, which is our 90 billion light year diameter bubble that we can see. But there's almost certainly stuff beyond that, right? It would be a ridiculous coincidence if all the stuff that we can see based on the age of the universe was also the edge. So it probably goes beyond that. The universe itself might be infinite. And at that point, talking about a universe touching another universe is hard to know what that would mean. If there are the other universes, like I know I talked about these sort of multiverses, if there are genuinely multiverses, it could well be that they are either separated by the most enormous gulfs of space or even just other dimensions. So it's difficult to imagine how they could touch our universe. There are some people, Roger Penrose, who's a theorist down in Oxford, has theories that the universe, sort of near the Big Bang, the universe might interact with nearby universes, and he made some predictions that there would be patterns in the CMB left over from these universes bumping together just after the Big Bang. But as far as I can tell, those patterns have not been found, so I think his theory remains a theory. So yeah, I think my answer is that there are some theoreticians that think this could happen, and they expect to see stuff in the CMB, but we don't see those patterns, and it's not a mainstream view, I think.
I'll take this question here then.
If gravity is something which inherently tends to act on mass, how could gravity be acting on the universe, pulling it inwards, if the universe doesn't really have a mass itself?
Oh, good. Yeah. So the answer is gravity doesn't just act on mass. Gravity acts on everything, right? So, in like a Newtonian model, then gravity is a force which acts on mass. But in the sort of the updated Einstein version of gravity, gravity is the curvature of space, and it affects everything. So, famously, for example, photons are affected by gravity, even though photons are massless. So, if you have a massive cluster of galaxies, it will bend space around it, and then objects behind the cluster will have their light sort of refracted and distorted. It's called gravitational lensing. So massless things get affected by gravity just as much as mass does.
When you say that dark energy is getting stronger and stronger, and like the universe is expanding, accelerating, is it like constantly accelerating, and is it getting like stronger exponentially, or is it constantly growing?
I think that's one of those questions that we don't know. We see evidence for expansion. I think actually measuring the rate of acceleration, I think, is one of the things that Euclid wants to do, because it's a very tricky measurement to make, right? Because yes, we know that the universe is accelerating because of dark energy. And the strength of dark energy increases over bigger volumes, right? So between us and the Andromeda galaxy, 2.5 million light years away, dark energy is basically negligible. You have to look over basically the entire universe, billions of light years, to see the effect of dark energy. But once you're looking billions of light years away, you're also looking back in time to when dark energy was less strong. And so you sort of have to sort of trade off these effects. And so what we actually see, like the observational facts for dark energy, is that when we look about 8 billion years in the past, we see some supernovae that are a bit further away than they should be. And so that tells us there's an acceleration there. But I think the whole thing is based on, I think, a few hundred supernovae. So we know the effect is real. I don't think at the moment we have enough data to say things like that. So that's one of the things we're hoping Euclids is going to be doing. There's another survey called the Dark Energy Survey, which has been running for a few years now, and I think they're hoping to ask that question at some point in the future. But as far as I know, they haven't done it yet.
There's a hand up there.
If the rate of expansion of the universe keeps accelerating, won't it eventually reach the speed of light, at which point it can't accelerate anymore?
Okay, so I'm going to say something that might sound crazy. The universe is already expanding faster than the speed of light. So there's actually no speed limit to how fast space can expand. So we obviously think of the speed of light as being the speed limit of everything, right? But what the speed of light refers to the maximum speed that an object can move through space and time, right? So if I throw my water bottle, the fastest I can throw this is the speed of light, because it's an object moving through space and you can't exceed the speed of light. But galaxies, when we see galaxies being carried away by the expansion of the universe, they're not really objects moving through space. We kind of pretend they are because it makes the maths easy, and we calculate the Doppler effect on their light as if they're just traveling away from us. But they're not really traveling through space. They're literally being carried away by the expansion of space itself. Like there's no sort of net movement through space. It's just space itself that's growing. And there's no speed limit to that. So we actually don't have to look very far away. And then if you come across this idea of redshift, the way astronomers measure distance, once you get to about redshift 2, which is looking maybe 10 billion years in the past, anything beyond redshift 2 is traveling away from us faster than the speed of light. Like as an analogy, maybe if you those little motorized carts you get at airports, like one of those might have a speed limit of say 10 miles an hour or something, and that's the absolute speed limit of that motorized cart. It can't go faster, except if you go onto one of the motorized walkway thing, you could easily leave a person behind you faster than 10 miles an hour. It's not because your car is breaking the speed limit, it's that you're just being carried away by the floor. And that's what happens to the universe. So yes, it can and is expanding faster than the speed of light.
Okay, did you still want to ask your question? Okay, we've got last 2 questions, I think.
So basically, in the time between now and billions of years in the future, when there's only one atom in the observable universe, obviously at some point that has to be affecting Earth and planets and such. But what actually happens to the planets? Are they just ripped apart until they're just atoms?
So I think my answer would be yes, probably, maybe, with the caveat that we don't understand dark energy well enough to answer that question. As of right now, the electrostatic forces that hold objects together are just trillions of times stronger than the forces due to the expansion of the universe. And so, yes, there are some models of dark energy where the dark energy gets stronger and stronger and stronger and eventually pulls apart more and more things. So it would start by disrupting galaxies, and then, a few million years later, it would pull solar systems apart, and then a bit later it would pull planets apart, and then eventually it would pull atoms apart. There are models of dark energy that say that it does that, and I guess it would eventually end up pulling even subatomic particles apart until you have just nothing but smooth energy flying away forever. There are models of dark energy that say that's true, but right now it's all theory, right? So it's hard to know what's actually real.
Something of a limitation on observations if the universe is only atoms big, really. There was one more question, I think, down here. Was it you? Okay.
So if, as light from other galaxies comes towards us, if its frequency decreases, if the energy of a photon is related to its frequency, where does the energy go?
So the energy just gets spread out over more volume. It's the same amount of energy, just spread out in more volume. The same way if you take an amount of squash and put it in a pint glass, and then dump that whole thing in a swimming pool. It's the amount of squash per volume has gone down, but there's still the same amount of squash. Same with energy. There's still the same amount of energy in the universe. It's just being diluted over a bigger and bigger and bigger volume.
Okay. I think we're going to need to finish because it's coming up to 7 o'clock. So I think we've had lots of very good questions there from you all. Some excellent answers. What do you say?
Thank you. And just to be really self-promoting for one moment, if you find this interesting, like I do, the book I'm all about this is called The Invisible Universe, and it's basically about all the stuff in the universe we can't see. It starts off from like infrared astronomy and gravitational waves, and then goes on to dark energy, dark matter, the future of the universe, all that kind of stuff. So today's talk was a small part of one of those chapters. So if you enjoy it, there's more.
Okay, we do want to finish. I just want to, just one more thing before you go. Can you listen, please? Firstly, if there's someone called Angel in the room, I have your ring. You can come and collect it later. It's a ring with the word angel written on it, so if someone's left it behind. These lectures are put on by the Cambridge Physics Centre. The Cambridge Physics Centre is staffed by volunteers, and we have our AGM coming up on the 8th of February. If you're here as a teacher and you live locally and you are interested, or even not that locally, I live in North East London, and you'd like to help us put on next year's programme, please talk to me afterwards, and I can tell you more details about the AGM. The next lecture is on February the 21st, and it's from Holger Bempinski, and he's going to be telling us how wings work, so I hope to see many of you there. Have a safe journey home.